Structures are objects that consist of one or more variables. They are usually of various types, grouped under one name for convenience, which helps with the organizing of complex data. In other programming languages, structures are often called records. A typical example of a structure is a point in a 2D space. It is represented by a pair of x and y coordinates. Another good example is a rectangle, which we can describe using 2 points. The LL point represents the lower left corner of our rectangle, and the point its upper right corner. We can easily initialize each sample structure. For the point sample, the code would look like this. In this case, the PL variable represents the point at 0, 0. For the rectangle with its lower left corner at point 0, 0 and its upper right corner at point 10, 5, the relevant declaration and initialization would look like this. It can be written in an even simpler way without using any auxiliary variables. In structures, we can also use the computed properties and functions. For instance, we can see our rectangle structure with 2 additional computed properties, width and height, as well as one area method, which calculates the area of our rectangle. Structures may also have their own initializer, which we'll discuss further in the course. At first glance, structures look very much like classes. However, there are 2 fundamental differences between classes and structures. First of all, structures must not inherit from other structures. The second difference concerns passing values. In classes, values are passed via references, pointers. In the case of structures, values are passed by a value. Their copy is created. Enumerated types, also called enums, are a very useful element of modern programming languages. It's a type of data that includes a predefined list of values represented using enumeration literals that a variable of this type can assume, hence the name. If you haven't dealt with this type, the definition might look a little bit convoluted, but the example will surely explain everything. In the example, we can see an enumeration type, a season, which is based on integer values and defines 4 values: spring, summer, autumn, and winter. We declare the variables or constants of the enumeration type and assign the desired values to them the way we declare the variables or constants of standard data types. And so we have the name of a variable or a constant, its type after a colon, that is season, and the assignment of the winter value. Referring to enumeration variables is also very simple. In the example, by using the if expression, we can check whether the season is a winter, and if so, we display the text "Get a warm jacket" on the screen. We can assign a value to each name, which is part of an enumeration type. In our case, the type is based on integers, and its subsequent elements assume values from 1, that is spring, to 4, that is winter. The raw value of an enumeration variable can be read by using the toRaw method. We can also use other data types as enumeration type raw values, for instance, characters or sets of characters, that is, strings. If we decide to base our enumeration type on numeric values, we don't have to specify the raw values at all, as long as we don't need them. A word of warning, though. Raw values are required if we decide to use, for instance, a character type or text. In the next example, we can see that I entirely skip the raw values during the type declaration. Interestingly, the raw value displayed for winter is 3. This is because, as a default, each element of an enumeration type based on a numeric data type, such as int or double, has a raw value assigned starting from 0. In our case, it is the value assigned to spring as a default. In the final example, we can see a slightly simplified notation, which we can also use. In Swift, when assigning values to enumeration variables or reading their values, we can skip the type name entirely and start directly from the dot. In our code, it simplifies both the initial assignment of values as well as checking them in the if block. To finish the subject of computed types, let's look at a slightly more complex example. It comes from a presentation at a 2014 Worldwide Developers Conference that introduced the Swift language. The example demonstrates two elements which are seldom found in other programming languages, namely initializer with the init method and computed properties. The train status type you can see may assume two values, on time and delayed. In the second case, we can also specify how big the delay of our train is. Now let's learn something about generic types. Generic programming makes it possible to write code without any prior knowledge of the data types the code will work with. Let's look at a simple example. Imagine a function that substitutes two values with each other. In our example, these are two character strings that represent names. We can clearly see how the values assigned initially to the variables are substituted with each other. Now, if we wanted to perform a similar operation on real numbers, we'd have to create another variant of our exchange value function, like the one shown in the example. The functions are almost identical, both the one operating on strings and the current one that uses the double type. The only real difference is the input data type. Generics come in handy in such situations. This is what our function would look like if it was based on a generic type represented by t. In both cases, we can see that the variable values were replaced correctly. By using a generic function, we simplified our example and avoided code duplication. The code becomes reusable so we can use it regardless of the type of data. The final subject we'll deal with are extensions that allow enhancing types with useful functions which aren't there in the standard set of functions of a given type. If you've programmed before in Objective-C, extensions are very similar to Objective-C categories. We can extend any named data type. In the example, we can see a simple structure, rectangle, which consists of two elements, width and height. Below, we expanded it with the increase n times method, which modifies the size of our rectangle based on the passed argument. The mutating keyword that precedes the function definition is something new. It introduces additional protection to our code and means that the defined function modifies the values it operates on, the internal values of classes, structures, and so forth. If we try to execute it on a constant, the compiler will send a warning. Of course, we can add extensions to existing types, both from Swift and Objective-C. In the example, we can see an extension which is very similar to the one shown before, but defined for the CG-size type. Another interesting example is an int type extension with repeat n times, which repeats the given task exactly n times int. In our example, the text Welcome to the World of Swift will be displayed 25 times. That would be all in terms of an introduction to Swift. If you're interested in this language, you can find more information about it on the Apple programmer sites, developer.apple.com, or in the next practical part of this course. Additionally, there are 2 books by Apple available on iTunes. The first one, The Swift Programming Language, is intended for all Swift programmers. The second one, Using Swift with Cocoa and Objective-C, focuses on the application and integration of the new language with Objective-C and Cocoa Touch. Both books are highly recommended. Thank you for your attention and see you in the next part of the training course.